Okay, we're now on page 720, number 27, section 10.3, arcs and chords. Roberto is designing a logo for a friend's coffee shop according to the design at the right, where each chord is equal in length. What is the measure of each arc and the length of each chord? Alright. If each of these chords is the same length, then each of these arcs will have the same measure. So if there are 4 of them, and they're congruent, and a full revolution is 360, then 360 divided by 4 gives us 90 degrees for each one. So we have 90, 90, and so on. So the first part, what is the measure of each arc? Each arc is 90. And the length of each chord. So now we want to find the length of a chord here. I know that my diameter right here is going to be 3 feet, because straight across from that we have 3 feet here. So if this is 3 feet, then this will be 3 feet. So if that's 3 feet, then I want to find the length here. Well, I know that this is a right angle, and my hypotenuse is 3 feet. These two angles have to be congruent, which means I have a 45, 45, 90. So in a 45, 45, 90 triangle, where the hypotenuse is 3 feet, and the legs are the same, so to find the leg, I want to take the hypotenuse and divide it by the square root of 2. So 3 divided by the square root of 2 is approximately 2.12 feet. And that's the length of each of these chords. 2.12, 2.12, here, and this one. Number 29. Write a 2-column proof of the indicated part of Theorem 10.5. In a circle, if 2 chords are equidistant from the center, then they are congruent. So first we need a diagram for this. Perpendicular here, so that represents the distance from the center to the chord. And we're given that that distance is the same. So we'll call this circle L, and call this F, G. Call this point X, and this point Y, J, and H. Okay, I'm also going to pencil in just a couple of lengths that we're going to consider in this proof. So this would be the radius from L to H and the radius from L to G. So those 2 lengths will be the same. And so let's state our given information. So in a circle, if 2 chords are equidistant from the center, so in circle L, LX is perpendicular to FG. Remember that the distance from a point to a line must be the perpendicular segment from the point to the line. LY is perpendicular to JH, and LX is congruent to LY. Then we want to prove that FG is congruent to JH. FG is congruent to JH. That our two chords are congruent. So given that this distance is the same as this distance, we want to prove that this length is the same as this length. Two-column proof. Alright, we'll start off with LG is congruent to LH. Because radii of the same circle will always be congruent. Okay, so with that said, let's state all of our given information. So LX is perpendicular to FG, LY is perpendicular to JH, and LX is congruent to LY. So next, we can say that LXG and LYH are right angles by the definition of perpendicular lines. So if we know that our lines are perpendicular, then they're going to form right angles. It's kind of just intuitive, basic information, easy to derive from this. Definition of perpendicular lines. Perpendicular lines always form right angles, in other words. Let's see, for number 4, we can say that we have some congruent triangles, because what we've shown so far is that we have right angles, so we have right triangles. We're given that XL and LY are congruent. We also stated that these two lengths have to be the same because they're the radii of the circle. So those two radii are our hypotenuse, and these two sides are our legs. So by hypotenuse leg, these two right triangles are congruent. Okay, and by CPCTC, we can say that XG and YH are congruent. So XG and YH are congruent by CPCTC. Corresponding parts of congruent triangles are congruent. And if they're congruent, they'll have the same length. by definition of congruent segments. And if I take that equation, I can multiply both sides by the same thing. So I can say 2 times xg as long as I say 2 times yh by multiplication property of equality. Let's see. Next, we can say that Lx bisects Fg and Ly bisects JH because a radius will be perpendicular to a chord only if and only if it bisects the chord. Okay, so let's have a look at that. In our diagram, since we know that our radius that goes through here is perpendicular to this chord, then we know that it'll bisect. So at x, that would be the midpoint of this chord. Likewise, y will be the midpoint of JH. Therefore, FG is equal to 2 times XG, and JH is equal to 2 times YH. And that's by definition of a segment bisector. With that said, we know that FG is equal to JH by substitution. So what are we substituting here? We're substituting in place of FG in place of FG we can substitute 2 times XG. So back in statement 7 we can substitute FG in on this side and JH in on this side, since we said that they're equal in step 9. So we can say that FG is equal to JH by substitution. Finally, we can say that FG is congruent to JH by definition of congruent segments. And done with that. And we'll have to get the rest on the next clip.